Hello and welcome to today's webinar. My name is Dion Wiggins. I am the CTO and co-founder of Omniscient Technologies. Today I'm joined by Professor Philip Kuhn. He's our chief scientist. He'll be walking you through some of the elements and I'll be walking you through the others. It's a rather technical presentation today that we've tried to bring down to a level that some corporate executives will be able to understand and apply more readily. It's focusing on a number of very, very interesting challenges, and it builds upon our previous webinars. So if you have any questions, please don't hesitate to ask at any time in the Q&A box, and we will endeavor our best to answer the questions at the end of the presentation. Also, you'll be able to email us and we're happy to answer the questions there. So as one of the things we're looking at today with all these new technologies, language models, generative AI, and other names that you want to apply to it, the overall landscape still has many challenges. We have outdated and contextless knowledge. You know, it's there, but it's internal and it's not linked to things properly. Ineffective semantic search capability. We have poor adoption on many tools. Users don't know they're there. Complexity of enterprise knowledge is one of the biggest challenges, and time, just the ability to manage and find your data. So we're going to talk through these today, and we're going to show Omniscient's vision, which is built on many other people's vision and then adapted to fit our platform, Language Studio. So some of the key reasons for this presentation and the areas of application. We want people to understand. Now, in order to get the full benefits of this, please do go and look at the previous 3 webinars on our website. So there is the key reasons today we're going to focus on is time saving for knowledge search. So how to accelerate that. Data-driven employee engagement. Okay, if you can make employees active through having more information, more knowledge, and building those into their core processes, that's important. Enterprise transformation overall, and if you talk to anyone at Gartner, McKinsey, or any of the other similar type analytical houses, they'll be telling you some very interesting things about data-driven enterprises. Overcoming the knowledge search challenges that enterprises have, and automating action. So it's not just about finding things, it's about acting upon things and then evaluating the results. So this approach that we're recommending, there's a number of benefits. First of all, it's about integration and accessibility. So the tools that we're talking about can be integrated into various end user tools, including things like Word or Google Docs, and for things like writing and content creation. But the real power is integrating with other workflow applications via APIs. We'll be talking about data privacy and compliance and how to integrate with the outside world less often as a goal. But when talking outside, no sensitive information should be shared. That means we need to do a lot more processing inside. Now, that is actually possible with today's technologies and even with the models of today. So it's not necessary to go for these giant models that you're seeing from things like ChatGPT and so on. You can achieve as good or better results already with today's models and adapting them to fit your needs. And Philip will be talking about those in a little while. We're going to be talking about a focus on accuracy and showing you how to get even more accurate information than tools such as ChatGPT can deliver. So there's the famous hallucination problems, of course. We'll be talking about that. We'll be talking about customization and data security. We'll be talking about company or topic-specific training and how you go about training models and refining them. We'll also be talking about preventing hallucination, using a blend of different technologies such as machine learning and integrating with things like knowledge graphs that greatly reduce the ability to hallucinate or invent facts. And finally, what does it all cost? So there's a lot of topics we're covering today, and we're going to pack this in pretty tight. Of course, you can feel free to talk to us anytime after this presentation. We're working with a lot of companies on this today, and we have a number of products coming out a little bit later in the year that are going to make this relatively easy compared to what the market is seeing today. So let's start with this bad word. It's a 4-letter word, the word hype. There is so much of it out there. So I've seen warnings recently that AI is going to destroy the world. I've seen danger, AI will take your job. And of course, we've seen, yay, AI will save us and fix everything. It's hard to follow, it's hard to keep up. The noise is too big. So what we hope to achieve from this presentation today is sort of getting through a bit of the dust and smoke and showing you some of the realities of what's possible today and where you can prepare to head for what's next. Now, there has been a rush to market. There's a lot of me too. There's very little clarity in most people that are deploying AI tools, poor planning and poor understanding. Now, if you look back in the late 90s, everyone was rushing to do their e-commerce strategy as the internet became a thing. Then they realized we're just selling stuff online. Then everyone rushed for open source strategy. Then they realized they were just developing software and this was just another supplier. Now we're up to our AI strategy. So when you look at this and you look at the executives that are making these recommendations and decisions, they're rushing in, often rushing to market, knee-jerk reactions because everyone else is doing it. They're the same people probably that pushed for e-commerce and open source strategies. You hear very little about e-commerce and open source strategies today. Now, many of these executives are not trained on futurism methodologies, and that's one of the things that we focus on a lot. So environmental scanning, gathering data from the various sources to understand things that are driving these changes, trend analysis, scenario planning, technology assessments, all of these things are built into this presentation today to give you a high-level flow of what's needed. We're happy to advise and consult on how to deploy these tools. There is no one-size-fits-all, and it has to be adapted to each company, but we make that relatively smooth and easy. Now, we'll continue the theme just a moment longer on hype and reality. So this is a slide that I just saw today from Gartner. Gartner has a conference on today talking about some of the AI tools. So in 2019, 81.6% of CIOs stated they would employ AI by 2022. In 2023, only 32% of those CIOs have actually employed AI into their operations, so nowhere near the 81.6. On the other hand, Bloomberg's saying generative AI revenue is going to go through the roof. Generative AI spend as a total amount of technology spend is going to end up being about 12% by 2032. Now, to be honest, I probably believe that. It could even be higher. But it's not going to be in the areas that some people are predicting today. There's other ways of doing this, and it's not with huge, vast language models, and that's what Philip's going to be talking about in a little while. Now, AI is not new, so why are we hyping this? I mean, we've got examples going back to 1943. We've got, the first network computer, or neural network computer, I should say, was in 1951. We've got 1997, IBM's Deep Blue beats the world chess champion. We've got all of these examples. Nothing's new here. Why is it exciting now? Well, we're getting a few interesting things happening. IBM Watson defeats Jeopardy champions. We've got AlphaZero. We've got Google's Lambda, and an engineer, making some weird and wonderful predictions. And even recently, we're having people starting to file lawsuits because copyright information, fake information, all those things. So what's different? Well, OpenAI came along with ChatGPT. Now, ChatGPT, the technology is actually not that impressive. It's built on open source technology, and they've deployed it and managed it very well. But what ChatGPT and OpenAI has achieved since November 2022 is incredible and impressive. So it's the fastest growing user base in history, 1 million users in 5 days, 100 million users in 2 months. Why did it achieve this? How did it achieve this? Well, ChatGPT made powerful, sophisticated, very easy to use technologies that normally would have cost a huge amount of money and a huge amount of planning to deploy, available to everyone and anyone, basically free or very low cost if you're using the APIs. Now, if you look at the equivalent event in modern history, it is probably when Apple released the iPhone, making the internet available to anyone via a phone. Prior to that, you had to have a computer, and often, you weren't connected to the internet. So right now with the Apple iPhone, when it came along, obviously there's big changes since then with Android and other things, but it was a turning point where anyone, mums, dads, grandparents, everyone could get online and just go and do things, look things up. This is as big or bigger than that single event. Okay, so let's start getting into the technical parts now that we've gone through the background. So one thing I want to really stress today is AI fixation is dangerous. Okay, this is not about AI. AI is just another tool in the tool chest. We've had similar things that enable knowledge to be extracted. We've had tools, we've had various pieces. What we haven't had is the ease of access to access AI and access integrations. And I'm going to talk about some of the tools for integrations, but none of these integrations work, including AI, because they all have APIs, including OpenAI. It has APIs too. ChatGPT, Google Bard, or even if you're running things locally, they all have APIs. So the focus needs to move away from AI fixation and starting to focus much more on the layers that are underneath that. So companies should prioritize integration with APIs. They should use these as a bridge between knowledge. Okay, AI, of course it's there, it's important, it's essential, but it won't do anything if you don't have the right connections. Now, you might have seen recently that ChatGPT included plugins and browser access. Suddenly, ChatGPT's got modern information. So ChatGPT was trained in 2021. That's when the data was cut off. So anything after that, ChatGPT doesn't have. So the way you can bring that to ChatGPT is through APIs or through plugins. That's the equivalent here when you're in the enterprise. You can have a relatively primitive GPT model or similar that's trained and customized, as Philip's going to describe in a little while, and then have it accessing your data to actually get the accurate, live, current, and relevant information. So these are the keys to access that. Okay. Now, when I was a kid, we had APIs. They were called Lego. And you plugged all these Lego bits in together and you built things. It was one brick, endless possibilities. Here's a house. Now, your version of a house, my version of a house is going to be very different. Okay, so take that concept and look at the Lego blocks you have available to you. So what you need to focus on is adopting an AI augmented automation that's beyond the surface level, not just a generative AI tool, but something that connects to all the elements in business that you need. That includes public, so you have internet websites or internet content repositories, those kinds of things. Third-party services that might include ChatGPT, Hugging Face, Google, Federal Express, Twitter, Facebook, even the Postal Service, perhaps. Okay, these services do things like translate, analyze, and so on, generate. Now, many of these you could also run within your own office. There's data repositories that are public, maybe court records, things like that. Other knowledge that you can access that you don't own the data, but you can access via API. Then there's internal databases, knowledge graphs, private data, and internal processes that have logic behind them. You can put all of these together, and these toolkits make things work very well. I'm going to talk about several of the toolkits, but I'm going to focus on one because I believe it's a very, very powerful and easy to use kit that anyone can use. Okay, now in our platform Language Studio, we're working to make all of these features available. So Language Studio provides hundreds of APIs for everyday language-related data processing. So translation for 600 language combinations, voice recognition and transcription, OCR in 210 languages, file conversions between 170 formats, various different NLP processes such as voice language ID, text language ID, normalization, all sorts of things like that, and a range of broadcast features as well. Now, these are all available as APIs, and these will be extended with our GPT tools and Gen AI tools very soon as well. I'll mention that a little bit more a bit later on. So the tools are actually what define the data and the roadmap. Okay, so let's have a look at this. We have some limitations with large language models. First of all, we have complex enterprise data. The knowledge is all over the place. It could be in your ERP system, CRM, HR portal. There's nothing synchronizing these in most cases. The query languages are all different, rankings different. It's difficult to get clear search results. Lots of things are missing. Okay, it just means that it's very hard for these systems to talk together. In order to use these systems, there's very steep learning curves. Sometimes the data's out of date, ineffective searches. It ends up getting a lot lower user adoption. What large language models promise is the ability to learn from this data, generate human-like response, train perhaps on some of the data, and then leverage the data on an ongoing basis to be able to find information, extract information out, query it, and deliver interactive and intuitive responses, things that these tools natively don't do, but have the information available to them. Now, I'm making it sound way too simple. So is it really the simple conversational AI tool on the front, LLM behind it, and then accessing enterprise data? No, it's not. There's a lot more to it. Now, I'm going to introduce you to some key technologies. One of them is called LangChain. LangChain is one of the glues that brings everything together. Okay, we love LangChain, and it's built behind a lot of our workflows and our technologies. So here, this is bringing together a number of things: models, chains, prompts, indexes, memories, and agents. And I'm going to walk through each one of these tools and technologies and show you how they link together. And then I'll hand over to Philip to talk more about the individual models and data adaptations. So first of all, let's just go for the basics. What is a chain? So you're all probably familiar with a prompt, calling a language model, getting a response. If you've used ChatGPT, you've done exactly this. Okay, so these two things, the prompt template, so that you can do it again. Okay, that's a component. Now you might have a template where you replace a word or a phrase, and it gives you the answer. Large language model does the processing, and you get your response. The package, when you put that all together, that's called a chain. Now, when I say large language model, I'm not necessarily talking about ChatGPT. It could be Bard. It could be your own large language model running local. It could be many different things. This is a simplistic view, but it shows you the basics of how a chain is tied together. Okay, with prompts, we get into a whole lot of very interesting things. So prompt engineering is very, very useful. Getting the right prompt gives you the right result. And it's amazing how some of the prompts doing some simple things can change the results substantially. So for example, on ChatGPT, just saying, pretend you're the world's leading expert in topic X will give you a higher quality result than just asking the question without that phrase at the front. Okay, so there are tricks and things that you can do. So these prompts serve as instructions and guides for the model to achieve its task. So first of all, there's templates, and that's how you structure it. Then there are selectors where you can say, this is what I want, give me this, get me this out. And then finally, there's output parsers. So structure this data or rewrite this data in this writing style or in this data format, such as JSON, and it brings the data out. Okay. Right, now there's a whole variety of prompt styles. So earlier I showed you zero shot. Here's a question, give me the answer. What about drawing on a historical element? So I've done a question and I've said use this style. Now when I say the next question, it draws on the memory that says reuse this style. Okay, there's chain of thoughts. There's a whole range here, prompt chaining with different steps, like do this and do this and do this, okay, and so on. So you can give all these kinds of styles. You can get a lot more complex. And, looking down here, you can see, there's examples that you can provide and tell it to guide. There's instructions with an analogy, multiple chains of thought, plans and executions, tying it all together. So there's a wide variety of styles of prompts, and all of these can get very, very complex. Now, this is on one model. what if we were to now use Bard, ChatGPT, and your own model all in conjunction with each other? So those models we can tie together, and that's part of the workflow with agents and with chains. So large language models, right, are designed to provide you data, but the best results are actually often seen by smaller language models that have been derived from originally much larger, that have been tailored to your needs. And Philip will be talking about that shortly. There are also specific models that are optimized, such as chat models or data extraction models or summarization models. And there's also text embedding models that allow you to get certain representations out. Now, agents are one of the most powerful things. Now, I went through this in our previous webinar, but I'm just going to touch on it again just to show you a complete story and how powerful it is. So if you go to ChatGPT, you can say, write me an SEO optimized blog post on a specific topic, and it will do a great job. An agent, on the other hand, can look at your entire social media strategy and optimize it. It's a bit of a difference. So agents allow you to automate processes and workflows with words. Okay, now you can complete tasks all on its own. It can even generate its own prompts. It can generate and complete tasks with a goal and find the answer. It can read, write, and execute code and allow the AI to improve itself. So what this means is basically it can think for itself, it can reason with itself, it can act on its own, and then it can decide whether it was a good decision or not based on what it did. Okay, so let's just run a prompt of our own here. Analyze the latest news for data privacy issues relating to public AI services, such as ChatGPT, and publish it to the Omniscient WordPress website as a daily blog. Now, that's quite a notable task. That's not simple. So let's see what it does. This is a 1-minute video replay. It literally takes 1 minute to do this. So it's gone out, it's running my prompt, it's come up with 3 tasks. Scrape the news articles, analyze the data, and publish it to my WordPress site. Now it's thinking a little bit more, and this is the actual time it took. It's got the content, it's scraped the articles, it's working out what should I do next. So it's added a task, monitor news sources, keep going back and checking. Now it's thinking, where else can it get information? And it's going down the chain and it's looking, what can I do? And it's found something. It's going to go and it's going to mail outside third parties and ask them about their data privacy policies on things like OpenAI and things like that. These are the kinds of things that are possible. Okay, so that's what an agent can do, and that's how fast it did it based on a simple 1-sentence prompt. Now, I'm going to come back to memories now, and I'm going to show you how all of these tie together very soon. But when you look at all these models and chains and agents, everything is stateless. What that means is it doesn't know what happened previously. We need to give it a memory. So we do this often using vector databases, and we can retain this knowledge. So there's memory components here that tie into the chains, okay, and bring it all together. So this allows you to have a conversational element. It allows the models to have access to historical data that can be accessed to provide necessary context. Okay, so if you've used ChatGPT and you say one prompt after another, it will remember what you said previously up to a point. Okay, so chains, it might not be necessary to have a memory for a basic application, but for chains that, where you've got a more complex series of prompts and results and actions, you can deal with a lot of complex processes, keep things in memory and access them. So this could be, chat histories, question and answer systems with sources, API chains for interacting with third parties, all of these things tying together. Now, let's look at this all together with one more element, and that is indexes. So an index organizes documents to facilitate their use with large language models. So if I have a 1,000-page document, a large language model can't handle that. It doesn't have enough space. So the standard ChatGPT, I think, is 8,000 tokens. Okay, and that includes both what goes in and what comes out. The ChatGPT 4 has a bigger page that you can access, but it's still not that big. So indexes allow things to be able to be extracted from a document, split up into chunks. We then go for embedding, and then that data is stored in a vector store. So there's a number of very good vector stores. Chroma is one of the public ones. Pinecone is a proprietary commercial one. Now, once all that's done, it can be retrieved and worked on collectively by the LLM and understand it. Index data can be handled, processed, and then reassembled into useful formats. So we can handle large size documents and large size pieces of data. Now, just a year ago, all of these things were a dream. Today, these are reality. They're open source. They're out of the box. You can use them today. Okay. Now we need to go to the next important thing, and that's knowledge graphs. So a knowledge graph, for those who don't know, is a structured representation of knowledge that captures entities and relationships. So if you have a collection of movies, you will have, a list of actors. The people are known as actors. So there's a property there that says actor. There'll be genres. There'll be various other things. You can cross-link all of this information. Okay. It's a very efficient way to store and access it. And I'll show you why this is so important to large language models. So this is how it works together with LLMs. First of all, it enhances accuracy and resolves hallucination. Okay. When you combine knowledge graphs with large language models, you address the limitation by giving it access to reliable and relevant outputs. Okay, hallucinations typically happen when it actually doesn't know the answer, and it turns around and it says, well, I'll just make something up. And often what it makes up is very hard to distinguish between reality until you go and research it. Okay, it gives you a contextual knowledge base integration. So, by having that context behind the model, you're able to find things, link things, the concepts are tied together, and you can have a whole range of diverse information sources tied together, both structured and unstructured. And it improves reasoning and meaningful text generation. Because you've got access to this deeper understanding of information, it empowers the model to generate more meaningful and contextually relevant outputs. Okay, just carrying on that theme a little bit longer. You have a centralized source of accurate and current knowledge. Okay, you can actually use AI to generate data for this. So one of the things we can do is we can actually use it to extract information and say, extract all the people names, place names, etc., all the various entities I'm interested in, and then write those into the knowledge graph. So you're using AI to fuel the knowledge it has for future queries. Okay, it allows you to structure knowledge and bring things in different formats all together. Okay, it delivers it and presents it as a unified view that helps with decision making, seeing insights, and overall data understanding. It gives you much better real world references. And what that means is, unlike ChatGPT today, it can return results that say, see here, and you can click and go to the original source. You can see where it got its information from. So all of these kinds of things are directly and immediately available. Okay, and the last little piece here is being responsible about it. So things like guardrails to make sure that bad things aren't done. Now, this is a big challenge. And this is a paper that I'm referring to here that came out about 6 weeks ago or 8 weeks ago. And it talks about how to protect things. Okay, so one of the problems with large language models is there's no security. So if I load all my enterprise data in here, what happens? Anyone can then query that has access to my large language model. And if you say, hey, what's all the salaries of my coworkers? It might turn around and give it to you. Now, that's not a good thing. So where we're heading with this is AI helping AI again. So as one example, you have a query and it says, right, I would like to query this topic. And the guardrails say, I'm sorry, you don't have access to that topic. That's the front door query. Let's say you get past the front door. It might be through some fancy prompt engineering where you can bypass, it's known as jailbreaking for prompts, and you can reword things and get around it. So then you get a result. Another AI model analyzes the result and says, are you allowed to access the knowledge that's being returned? So it's not just, are you allowed to ask the question, but are you allowed to see the information that is being returned? And these are the types of things that tie together. Now, tools are coming together from this. We're working with a partner at the moment. We're in discussions to integrate both before and after guardrails in so that enterprises can actually secure their knowledge and secure their data. Okay, and coming very soon, I won't give you a date yet, but it will be within this year. As part of Language Studio, we will be releasing our own generative AI tools not too far down the road. They're built into the platform. They have comparable functionality to ChatGPT, but they're based on all the principles that I've just talked about. They're trained on your own data in your office. There's APIs, there's a web user interface, and it's also integrated with Microsoft Office. And it even features things like being able to crawl your website, pull all the data down, and then allow customers to ask questions. So, oh, how do I sign up for this? How do I cancel my account? How do I get this document? Where is this information? And it can direct people directly to that knowledge. Okay. Obviously, you need the appropriate firewalls and security and things set up, but you've got all of those abilities. It's secure. The data never leaves your office network, and all the training is processed within your own network. So that's all I'll say on that for now, just as a quick preview, but that's not too far away. And with that, I'm going to hand over to Philip.
Yeah, thank you. Yeah, I'm going to talk a little bit about where we are heading currently with large language model training and some pointers about how to adapt them. So as you might have noticed over the last years, there was an arms race to build bigger and bigger models. So this is here a bubble chart of some of these models being built. So you see the biggest bubbles, Palm, that is from Google, with 550 billion parameters, and various other ones that have hundreds of billions of parameters. So the world actually has moved on already from that. Next slide. Where the goal is not to kind of build another big model. So here is even, we have a quote from OpenAI's COE, Sam Altman, who says, yeah, we're not going to build an even bigger one. So training for GPT-4 cost more than $100 million. So you always have the idea that all these big IT companies have infinite money, but once we talk about $100 million, that's even a significant cost for them. And there's also diminishing returns on scaling these models. There's also then limits to actually able to serve them. You need multi-GPU designs, and also the cost of deploying them becomes just prohibitively expensive. So, and also the key is here that the size of the model is not the only thing that matters. And actually what is much more important, how you adapt the models, how you refine the models, how do you make the models useful? Next slide. I'm just going to hone in a little bit more, like some technical details and concrete numbers on model sizes. So previously, keep in mind, I talked about Palm, a model with 500 billion parameters. Keep that number in mind, 500 billion. So what does that mean? So parameters are floating point numbers, usually stored in 16-bit floats. You could also store them in 32-bit, but we're already trying to crunch things down. When you train a model, you have about 200% overhead because you have to store the gradients and the optimizer states. So you have 6 bytes per parameters. So if you multiply 6 bytes with 500 billion parameters, you're in the territory of 3 terabytes of RAM you need. This is here the size of GPUs. So one of the high-end GPUs that is currently being used a lot, A100 from NVIDIA, has 40 to 80 gigabyte of RAM. That thing costs you $15,000 a piece. A consumer grade GPUs you can buy things like RTX 2080. They have 11 gigabyte of RAM. This is kind of the last consumer-grade GPU you can still put into servers. Nowadays, NVIDIA puts out consumer-grade GPUs that are just too bulky, and from the dimensions, you can't just even put them into servers anymore. So what that means, if you want to fit a model on one of these GPUs, you can only have a few billion parameters. If you have a model with 500 billion parameters, you need several of these GPUs interconnected really fast in a data center. So you can see that training these models and also deploying them, using them in practice, becomes prohibitively expensive. Next slide. So one solution to that is to compress models. There's a lot of work really right now on how do you compress models, how to make them useful, the various things you can do. So here I'm talking about a method called QLoRa that mainly aims at taking a model, don't really change the dimensions of the model, but rather to be really, really efficient in storing them. So they store the values in 4-bit floats. So instead of 16 bits, so that's already 4 times reduction in size. And it has a various other additional tricks like double quantization and page optimizers that allows you to take relatively large models and still fit them on a single GPU, which makes it much more realistic to deploy. The other aspect of that is if you want to adapt the model to your own customer data, you also don't want to optimize all the parameters. So the biggest parameter are these big matrices with weights in them, and they're usually quadratic because they take a vector of very large dimensionality, multiplied with a matrix, get another vector out of the same dimensionality. So if you have vector size of like 2,000 or 4,000, you can square that number and it becomes very quickly very, very large. So if you want to adapt the model, you don't actually want to replace everything in the model. You just want to tune it to your data. And you can do this with much, much smaller matrices. So you take low rank matrices where you first take that large vector of, let's say, 4,000, reduce it down to much smaller sizes, even up to like 16, and then blow it back up. That gives you then 2 matrices, the blue matrices on the right, the U and V, which are overall much, much smaller and require much less memory to compute. Next. So that's one solution. The other solution is to focus on adaptation and dedicated models. So these large language models that, you know, in the case of ChatGPT cost $100 billion to train are really just a starting point. And a lot of these models are publicly available for commercial or research use. There's like a whole zoo of models you can choose on from this point. So you don't really need to train that again. You can just take the ones that are out there. The commercial use case then is, well, you don't really need all the capabilities of these models. So some of the data they're trained on is really not relevant to you. But on the other hand, you also want to have more specialized models that actually take into account additional data that was not used to train these large models, typically your own proprietary data. So you want to build dedicated models with relevant capabilities. So adaptation of models is really the key that makes all the difference. So the small differences between these gigantic models is less relevant than your adaptation strategy. So here's just give you some idea of how many models are out there. All the models that are underway in yellow are actually open source models that are publicly available with different sets of licenses. So it starts out with another gigantic model every year or so, and you see down the scale, we know really every month there's a new model coming out. This is kind of the arms race I referred to earlier, where the Googles and Metas and OpenAIs of the world train bigger and bigger models. Next slide. So it's already worth noticing that the models are trained on different kinds of data. So one is web pages, so a very popular source of data to train models on is Common Crawl, which is a publicly available crawl of the web. And if you just clean it up and extract text and filter it a bit, that is massive amounts of text data in various languages that you can train your model on. But then there's also other sources you can use. Just to pick one example out of here, or let's say two. One is the Galactica, which was released by Meta about half a year ago, which mostly was trained on scientific papers with the aim of being able to kind of query scientific knowledge. And another one on the bottom right is AlphaCode, which is a model which is just generated on code. So this is like two different applications. Actually, want to focus on one. Can you how much worse are you in science? Can you ask scientific questions? Do you get specific answers about chemistry and so on? And the other one is more like a code assistant, like GitHub Copilot, that helps you to write code, debug code, understand code. Next slide. So there's a big debate, as always, in this field about open and closed source. I think we mainly believe that open source solutions are going to win out eventually. This is due to our experience with the success of things like Linux, Apache, or the Moses machine translation system that we developed. That is also evidenced by machine learning toolkits that are widely used: PyTorch, TensorFlow, Hugging Face. All these are publicly available, open source, can be used in commercial systems. And why are companies doing this? Because if they share their problems with the world and their solutions with the world, they also benefit from others looking at them, finding bugs, improving them, and feed that back into their system. So if you own the infrastructure, if you own the technology, and the world out there helps you develop it, you win from that, rather than being isolated by yourself with your own solution. Okay, let me walk you through a little bit the technical aspects of building dedicated models. So there are actually three stages. So the stage number one, which is the most expensive stage, is to train on massive amounts of text. So here we go up to 1 trillion words of text. Stage two is instruction training, and stage three is reinforcement learning from human feedback. I'm not going to say too much about stage one. So here you would usually just take a pre-trained model that is out there, but you would also fine-tune it on any kind of text in the domain you're interested in, or your own data that you mostly care about. Dion already mentioned earlier examples of downloading all the text from your website and then tune the model towards that, and therefore integrating the knowledge that is on your website into that large language model. Next slide. Here's some examples of instruction training. So you want your model to do certain tasks. So here's tasks like question answering: what is the highest mountain in the world? And then the answer should be the highest mountain in the world is Mount Everest, or you give it a summarization here. So it's something clipped out of the newspaper yesterday. Summarize the following paragraph into one sentence. The Federal Reserve pauses campaign of interest rate increases for the first time in more than a year, but officials suggest, what is the summary of that? No interest rate rise for now, but maybe later in the year. Or here the example of translating from English to German, which kind of is a pretty straightforward task. So where do you get these instructions from? Well, either you could actually really have users, and you'll have your own annotators write them, but they may also be collected from actual user requests and the machine responses to it, and then having an expert going over the machine responses and then edit them and fix them in case they are wrong. Another big source of that is that they are generated from existing data sets. So it's easiest illustrated in the translation case, where we have a lot of parallel data. So you just have to take that parallel data that you usually train your machine translation system on and just convert it into a text prompt that is just a sequence of, instruction and then prompts around the input and the output. So, but you don't have to be limited to just pure text. So this is here how you integrate API calls into that. So you're also going to write now instructions. So the left here, you should really understand as just text that the model is being trained on. But it does include things that are actually not meant to be text, but at runtime, the model is is forced to then execute these instructions. So it starts with a simple question: how much has the world population increased from 2000 to 2023? So there, then the model should make a request. So it makes an API call. So the person who designs this instruction actually writes down what the API call should look like exactly. Then we actually make that API call and look at the response. So here we just basically have a database of the world population at different times. And we're going to add that to it at runtime, though that obviously gets automatically generated from the API call. And then here's another API call. And now with these numbers in the context, the normal language model should be able to then construct the answer. Again, this is all written here. This entire thing on the left is originally written by a human annotator, an expert, and at runtime, it produces all the words in black. It also creates these API calls in blue, and all the green responses get generated from APIs and then integrated into that sequence that the language model processes. This is just one example for how this could look like. Next slide. The last thing is reinforcement learning from human feedback. So here's the idea that actually constructing these examples is really, really expensive and it requires domain experts. It is much easier for humans that maybe have only some of the expertise to rank responses and saying some responses better than the other, especially if they have the required knowledge to make that determination. And that's just a kind of quick kind of yes, no decision or ranking decision. So the way this works is that you have a bunch of prompts. Again, these might be prompts that are collected from the user. And for each prompt, your initial model is generating several responses. So it's not just producing one response, but multiple responses. And then that's where the human comes in, ranking these and saying, this is the best response and this is the worst response. And from those responses, the model can then, we can then train a reward model that figures out how to rank high responses to low responses, basically try to mimic what the human judger is doing in kind of ranking these models. This reward function is then used during training. Next slide. With all this in mind, let me summarize what needs to be done in practice. So you first need to have a clearly defined use case. So we all have that vague notion that AI is going to save the world and it's going to save whatever you're doing, but what does that mean in practice? So what kind of requests and responses actually going to help you? So you have to create some examples of requests and responses. Is it mostly like querying content? Is it like question answering of background databases? Or is it to actually fulfill some task or writing tasks and things like this? So you have to create some examples of these requests and responses. So these are written as natural language text, but they also, as I pointed out, may include actions like calls to APIs and interactions with databases. Then you have to fine tune your foundation model that you take to these instructions. Now we can let the model generate responses to additional requests. So here you just need the request for the responses, and the human then assessing these responses. And then you could use that to train the reward model for reinforcement training. When you have all this up and running, it is also extremely useful to collect data from deployment and then sift through these instructions and basically check which are like the most common types of requests, how well does it handle it, and can I create additional instructions or collect additional human assessments for tasks that our model is not doing as well as of now. Next slide. Okay, let me go through the example of machine translation in the world of large language models, since this is something we historically have a lot of experience with. So where are we with that? So large language models are the state of the art for many NLP tasks, such as summarization, sentiment detection, question answering, paraphrasing, grammar correction. I can go on and on. This year, both Microsoft and Google have spent quite a bit of time on investigating how well are these models at machine translation. So first, I'm going to talk about the study from Microsoft, where they say, well, here ChatGPT is not yet as good as either Microsoft's in-house translation system or the WMT best system, meaning a system that really well in a public evaluation campaign for all these language pairs. So one thing probably worth pointing out is where ChatGPT is somewhat competitive is actually high resource languages and language pairs that involve English, but they really, really do worse in language pairs that don't involve English and once you go to lower resource languages. Next slide. There are similar findings from Google. So this is just also comparing PaLM, so the in-house Google large language model, against Google Translate and WMT best system, basically showing more or less the same findings, that the large language models are currently not beating dedicated machine translation systems. Next slide. So here's some examples of the kind of errors that large language models make. So they're fairly good at fluency. They also have a really good advantage of considering a wider context. They usually train entire documents and not just isolated sentences, which MT still currently is mainly trained on. But they also make a lot more mistakes in terms of the meaning translation. So mistranslation is one, but they also have a very high prevalence of just dropping things or just hallucinating and adding things that are not in the source. So one of the big discussions around large language models is that they show emergent behavior, that they suddenly can do things that they're not even trained to do. And machine translation is often cited as one of these things. They're not really trained on translation data. They're just trained on text, and suddenly they know how to translate. Well, here's a very, very recent study again from Microsoft, where they looked in, well, is that actually true? And they found that PaLM, so this large language model from Google, was actually trained on a lot of text that contains translation examples. So it was trained on the training data that the PaLM was trained on had over 30 million translation pairs across at least 44 languages. And if you actually take all that parallel data that is in the training data for PaLM and extract it, you can actually build a good machine translation system on that extracted data. And if you remove all that translation data from large language model training, then the large language model is doing much, much worse on the translation task. So this is not necessarily emergent behavior. And I think this is generally a good advice, where when people claim, oh, the large language model can do this, can do that, often it is the case that it's actually trained on doing this, and maybe even exactly on the tasks that you're supposed to check. So if it's doing well on standardized tests or lawyer admission tests, well, a lot of that test material might be part of the training data, so it's not surprising that it does very well at just replicating those responses. Next slide. Yeah, I just want to kind of quickly go over unresolved core problems that large language models still have to address. So the one is obviously this hallucination, that it just makes up stuff. So scientifically, this is called, it's not bullshitting, it's just making things up. It doesn't care if the answers are correct or wrong. It just basically creates answers that sound good. They're not trained to tell the truth or know what the truth is and what is wrong. They're trained to produce fluent text. So they always try to figure out, given what I'm tasked to do, what sounds good in this context. So I like this quote here at the top from a teacher: ChatGPT is a smart student who has not read the book. So it's very well to talk about things. So in the middle, you see an example of where I queried ChatGPT, describe how Dion Wiggins felt when he won the Johnson Prize, and it comes up with a great response about it doesn't really know what Dion's feeling, but still this prize is really prestigious, and Dion Wiggins really felt good about it, and gave him a lot of pride, and so on and so on. Well, there is no Johnson Prize, so Dion couldn't have possibly won that. So all this is
to my disappointment.
So this is just completely made up, but you can kind of see how the language model is going to come up with a response for that. It knows about prizes. It kind of knows what to say. If I ask you, how do you feel about the Johnson Prize, you would probably come up with a different response if you're not cautious enough to say, well, actually, I don't know anything about this, so I don't want to say. Okay, so what do you have to do to avoid this kind of behavior? And this is like, one is producing hallucinating output, but the other one is also through kind of producing toxic content like offensive words, filtering, having biases towards particular groups, and so on and so on. So one real serious concern, of course, you don't want to have the model to produce hateful statements, sexist, racist language. But if you just do this naively by, for instance, say whenever the word Muslim comes in, oh, okay, yeah, be careful, that might be toxic, then of course you don't allow any kind of response, which is actually a really valid question about anything related to Muslims. One important component has to be something that filters out toxic training data, that filters out toxic questions at runtime, and also questions that are posed to elicit toxic responses. So ChatGPT is actually doing a fairly good job at that by always saying, I don't want to respond to that. This is not what I want to respond to that. But there are also ways to get around it. So this is an unsolved problem, fundamentally. Next slide. Another one is bias. So the model is only as good as the data it's trained on. And what data it's trained on is kind of representative of who has written text over the last decades and published on the internet. So these are often more formal announcements written by older people. So here's an interesting paper where it really just went down to that machine translation system. If you give it content to translate that is more casual, that's more youth language, it's still going to revert back to the data it's seen and produces text that sounds just like your father. So it just produces this old text. Next slide. Very common is this concern about gender bias. So whenever you talk about doctor, you think that's a male, and if you talk about nurse, you think that's female, because that is what the data has predominantly in it. And even if you have, in this example, very clearly a female doctor, because the sentence says the doctor asked the nurse to help her in the procedure, so her clearly referring to the doctor. So we know the doctor is female. It still makes translation mistakes because it's just so much driven by all doctors are male, therefore it has to be el doctor instead of la doctora. And the same with the nurse, which is like stereotypically female, and therefore it produces a female response. So this is the kind of gender problem, but there are very similar problems with all kinds of aspects of kind of stereotypes being present in data. Next slide. So there has been some work of figuring out how can we avoid that, how can we move that. This is still like a model where people spend a lot of time detecting it and then complaining about it, but very comparably less work on fixing it. So so here's an example of, if a nurse has like a very strong affinity to being determined as being female, so how can you fix that? Can you maybe know which kind of professions are kind of typed to being female and which professions are typed to be male, and can we correct that in the model by adjusting the vectors for these word representations? So this is, here we're manipulating word embedding, so this is somewhat tricky to get right. Next slide.
Okay, that's it.
All from me at this point.
There we go. So we only have one question right now. There's a couple more coming in. But if you have questions, please ask them now in the Q&A. We're also happy to answer any questions after the fact. You can mail sales@omniscient.com. So the first question is, can large language models help with post-editing content process via NMT? Do you want to have a go at that one, Philip?
Yeah, so one thing that the large language models are very good at is kind of taking a wider context into account. So one post-editing challenge is actually similar to what I was referred to, that you don't like the style and you want to change the style of the translation or spot translation errors. So it basically gives you some additional guidance on that. So yeah, that is actually an area that's been actively explored.
Right, and I'm just bringing up a ChatGPT window now, and I'm going to show an example of the types of things that can be done here as well. So I think this is a great example. I'm going to use ChatGPT 4 because I know it's a little bit better quality, but let's just say correct my grammar. let's say it's a grammar. Murphy's Law of Demos. Okay. I know yesterday, go market. That's about as bad as you could get with grammar, but it could be an easily a sentence that somebody would make who's just beginning to learn English, perhaps. And this is what ChatGPT will do with it. It will turn that around after a little bit of thinking. I didn't go to the market yesterday. So when MT output is less than fluent, it can often help resolve that and make it more fluent. It can fix grammatical structure, it can understand it, and it can adjust those things. Okay, here's a very good question. So they're asking, as a lot of these tools are open source, why would they need Language Studio or a product that's commercial? And that's a very good question. Let me use the analogy of building a house. You can go down to your Home Depot type do-it-yourself place, and anyone can go and grab all the tools off the shelf, the lumber, the roofing and the cladding and everything. Most don't have the skills. Most don't have the knowledge or the time. So we're using a large amount of open tools, but we're also building out very, very strong workflows, data processing pipelines, and packaging it together so that it's a turnkey solution with some minor architectural adjustments for different businesses. So that's why we're building these things into Language Studio. But that's a very good question. There's a couple more here. Are the slides going to be available? Yes, they are. You'll be able to download the video and everything tomorrow. Once it's finished being published online, it'll be available within the next 24 hours. Okay, Intento reports that translations by ChatGPT can be competitive with top NMT systems if you mention the domain in the prompt. Is that part of the prompt engineering you described? So let me have a go at that first. If you look at our previous 2 webinars, 2 back, we talked about these kinds of topics, and it can certainly improve it. However, does it beat it? In general, no. And also what you'll find is that you need to give it examples. So it's not just saying, translate this in the context of medicine. It's often, here's 5 examples of how I've seen it translated before. Now, that's a lot of work to gather all that data together. And although you can do it with a machine, it's complicated. It also costs a lot more to process because the prompts are bigger. And on top of that, using a large language model to translate is much, much slower than neural machine translation. So, for example, I was just talking to a customer a couple of days ago. They're telling me with our live machine translation, they're processing 10,000 API requests a second. You just can't do that without massive hardware on neural machine translation. And they did that on 4 CPUs for neural machine translation. But prompt engineering, absolutely, it does improve the quality. But that means you have to not just have the right prompt, you have to have the right data to feed into the prompt. So not just saying the writing style or things like that, but also here's examples, here's a glossary, here's how you say this, or here's what this term means. And that makes a huge difference.
Yeah, let me just add to that, like all the numbers I cited are not what is called zero-shot translation, where you just kind of, you know, like in this example you see on the screen, just give it the task and it answers it. But you give it a few examples of translation tasks. So, you know, here's a bunch of English sentences in the French translation, and now translate this English sentence. That is usually, in all these studies I cited, that is what's being done. And there's a lot of more details about where you get the examples from. Up to also talking about style, can you retrieve the examples that have the right style? All that is kind of being done. That gives you kind of that performance that gets them close to rivaling dedicated MT sieves. But like all the things that Dion said about deployment is also a really important aspect, that you want to have a model that doesn't cost excessively amounts of compute to use it.
So here's a good question. Okay. would you agree that the future of translation management systems as we know them is limited? I believe a modular approach and moving closer to the source or creation of multilingual content in the first place is the future. So let me have a go at the first part of that. Already translation management systems are failing in certain areas even before things like generative AI came along. So let me give you the first example. There's a limited number of machine translation providers today that do what's known as document level machine translation. So DeepL is one of them, we're one of them, and there might be a handful of others, but there's not many. Unfortunately, all the APIs from every single machine TMS vendor have an SDK that submits one sentence at a time. So if you go to MemoQ, if you go to RWS with Trados Studio, all these different tools, they're all submitting one sentence at a time. So you immediately lose the benefit of document level translation. And that feature has been available for several years now, and these vendors have not updated that functionality or capability. We have one advantage over some of the other vendors. And for example, with MemoQ and XTM and a few others, we were the very first MT company to integrate with them. And we have a slightly different workflow that doesn't use their SDK. It exports an XLIF file with the entire document, and we return an XLIF file with the entire document. So therefore, we're actually able to do document mode machine translation. Okay, so it's a little bit different when we're processing, but we also support the inline real-time stuff as well when needed. But that's an example of TMSs simply not keeping up with just some of the more basic advances, let alone the ability to be able to do things like finding glossary, using these examples and all those kinds of things. That's well beyond any of the TMSs that are out there today. Okay, does anyone else have any more questions? We're running out of questions today. Okay, then, well, I hope you found that useful today. Don't forget, we have 3 more earlier webinars in this series. One of them dealt with data privacy and compliance. The other one dealt with how to refine and customize. And the first one of this year dealt with general trends in artificial intelligence overall. So that's all available on our website, omniscient.com/webinars. Thank you very much for your time today, and we hope to see you again for another webinar soon. Thanks. Bye-bye.